So one of the most important reactions that we see in aqueous solutions is acid-base chemistry reactions. So acid-base chemistry reactions require two parts. So you need to have an acid, something acting as an acid, and something acting as a base. So you can't be an acid unless there's a base. You can't be a base unless there's an acid. So we have a couple of these coupled reactions or paired reactions. We will also talk about oxidation reduction reactions, and in this case, we're looking at a transfer of protons or hydrogen. And in redox chemistry, we're looking at transfer of electrons. So there's a couple different definitions of what an acid is, and so we'll go over both, and we'll stick to one after that. So we have first the Bronsted-Lowry definition. And that's simply, we're going to use HA to define a generic acid, where H is what's being transferred, A is everything else, and that if we put this HA into water, it can dissociate into H plus A minus, where a hydrogen without an electron is a proton and neutron, and so sometimes we simply refer to this as a proton. This is important because part of our definition is calling H plus proton or proton donor, so we need to be aware of that. And what's left is, because we took the H plus, we have A minus, and that will have, we call that our conjugate base. Okay, this reaction is a little simplified, and a better way to show this reaction that's more realistic, because H plus is very unstable, and this is actually happening in water. And so we have what really happens, and the best way to write these acid-base reactions is showing the water and showing that this oxygen is going to take this proton, and the electrons are going to go to the acid, and so we get H3O plus A minus. And so H3O plus we call hydronium, or the hydronium ion. So this is important simply because in this class we say that H plus is the same as H3O plus. It's just a definition, or not definition, it's kind of like a shorthand instead of writing H3O plus. But H plus is very unstable in water. And the moment that you create H plus, it's going to bump into a water in an aqueous solution, and it's going to make H3O plus. So H plus is, I always like to say, is kind of like the Easter Bunny or Santa Claus. It's something that your parents told you that was real, and sometime down the road you realize actually it doesn't exist. It's actually your parents. H3O plus is what's actually floating around in solution, and so we tend to write that in our reactions. But if we do write H plus, it's actually, I'll put quotes around here, we know that this is just representing H3O plus. Okay, so just so that's clear. And then let me just, the hydronium ion, just to show you what it looks like. We have, so, okay. So, that said, we're going to then look at defining the strength of acid. So, I never actually defined. So the Bronsted-Lowry definition of an acid is a proton, which we call H plus, donor. And you can kind of see that up here, that we have the HA has put a proton into our solution. Okay, now this is not the most inclusive definition, and that's why we tend not to use it as much, but we can talk about one other thing, and that is that there is two types of acids. And so the acid is a, well, actually, sorry. The Bronsted-Lowry, the definition that I'm not going to even write is the Arrhenius definition. And that definition talks about donating an H plus or an OH minus, and that's not always the case for a base. So we will only use the Bronsted-Lowry definition, not the Arrhenius, just for point of confusion. So this is actually what we use. It's a proton donor. An acid will always donate or put an H plus or more specifically an H3O plus in solution. So we have two types of acids. We have weak acids, and we have strong acids. I think a strong acid makes more sense. I'm going to put a strong acid first. It's just a little simpler. So we'll do a strong acid, and that's what we've already written. And that's where we have complete dissociation. A strong acid is a strong electrolyte. And so a strong acid dissociates. So if we have HA, and we're going to call this a strong acid, plus H2O, that's going to have a one-directional arrow that shows the reaction only proceeds in the forward direction, and you get H3O plus A minus. So a strong acid, if you have 1.0 molar of HA, then you'll end up with 1.0 molar H3O plus and 1.0 molar A minus. So if you were to, again, example, I have like HNO3 plus H2O, you would make H3O plus NO3 minus, and if I had 1 molar HNO3, then I would have 1 molar H plus and 1 molar NO3 minus, because we define HNO3 as a strong acid. Now the strong acids that we need to know about in this class are HCl, HBr, HI. Those are your three halogen-based binary acids. We don't actually have HF. So HF is a weak acid, and that mainly has to do with its small size and high electronegativity. Fluorine is very special in that regard. So no HF, but we have HNO3, that's nitric acid, sulfuric acid, H2SO4, and we have perchloric acid, HClO3. Okay, so these are our strong acids that we'll need to remember. Strong, if you know that these are the strong acids, then you should be good to go to identify these type of acids in chemical reactions. Okay, so a weak acid, if we define a weak acid, we will denote that with the arrow being used. So a weak acid, again, I'm just using generic HA. We're not going to differentiate between the two, but we can show you it's a weak acid by giving you this equilibrium arrow showing that we can have both the forward and the reverse reaction. Now we're still going to have the A, well, let's do the same way. We're still going to have the H3O plus A minus. Now the difference is that if we look at the concentration of HA, it will be much greater than the concentration of either product, H3O plus or A minus. Now I just introduced this bracket term, so just so we're clear, this bracket term equals concentration. So if I have bracket X, that is equal to the concentration of X, just so we're clear. And so this is showing us that we have way more of our reactant that stays as a reactant or is converted to product and quickly goes back to reactant than how much product is made. So and this is varying on the weak acid, but in general, we would say that maybe for every 1 million HAs, maybe one goes to form H3O plus and an A minus, and you might say, well, that's not actually that much, but if you think that we have hundreds of millions of trillions of HAs, and 1 in a million actually produces enough to be measurable and to notice there's chemical properties of a solution that are different for weak acid solutions. So they do matter, though the scale of what we're talking about is actually quite smaller than we might assume. But still, it is a meaningful amount of product forming, so that's why we care about it. So we can talk about bases as well. So bases are also going to be in 2 flavors of strong and weak. So defining a base in terms of the Bronsted-Lowry definition is we call a base a proton acceptor. Now, a lot of bases have the hydroxide, but not all. And so this is why we're going to put there's 2 types of base. The first one that we see is a strong base. A strong base almost always, in this class always, will be with a hydroxide. And a hydroxide is always paired with a metal. So we have MOH goes to form, again, single arrow showing that it's strong, M plus OH minus. And so we'll note that this is a group 1 metal, and that this OH minus is hydroxide. Okay. We can also have, just to show you, it's also possible to have, for example, MOH2 goes to form M2 plus 2 OH minus, and this would be a group 2 metal because it has a 2 plus charge. And these are both strong bases. Okay, so strong bases tend to be, so if we look at the strong bases, we will see, let me grab my periodic table, they are going to be, we already wrote these out, but we can write them again. It is lithium hydroxide, sodium hydroxide, potassium hydroxide. Now those are all the group 1 metals. And then we have calcium hydroxide, strontium hydroxide, and barium hydroxide. Now you'll notice the 2 that are missing, I've written these as the periodic table is written. The 2 that are missing are beryllium hydroxide. These are all OH2. I'll go fix those. And magnesium hydroxide. Let me go back in red and give all of these the 2 hydroxides they need. Now, what's in blue, these are weak bases. And the reason why they are weak is because they have too strong of interactions between the beryllium and the hydroxides that when you put them into water, they actually much rather stay as an ionic compound because their ionic interactions are so strong. And so they do not dissociate completely as the other strong bases do. So again, I've just kind of written these. This is, if you look at the periodic table, you can see this is the ordering. But it makes it pretty easy to remember as long as you know that beryllium and magnesium are not strong bases. Okay, a weak base. So strong bases will have complete dissociation with an arrow. A weak base, just like the weak acid, is going to have incomplete dissociation. And so a weak base, we tend to see, we just write as B. And this is a weak base plus water. So this is where hydroxide is actually not being put into solution, but we still have a hydrogen being accepted by the base, and in doing so, an OH is still put into the solution, but it's not donated by the base, which is true here, where we actually have a metal donating the base. Here we actually are taking a hydrogen off of water, leaving a hydroxide remaining. So in a weak base, so this is weak weak base. The concentration of our weak base is much, much larger than the concentration of the protonated base or of the hydroxide anion. Okay, and so we can talk about these in terms of definition. So again, this is our base. This is acting as our acid. It's donating a proton. Then this would be our conjugate. Oh, conjugate. Oh, let's just redo that. That's a little sloppy. Conjugate acid, and this is our conjugate base. So we always have an acid and a base. We always make a conjugate acid and a base. The base becomes a conjugate acid. The acid becomes a conjugate base. Okay? Strong acids, strong bases are strong electrolytes. Weak acids and weak bases are weak electrolytes. All right.